Hello, everybody. My name is Mathieu Joerger. Welcome to this webinar here. I want to point out that I am in my home, and it is safe for me to take my mask off. I'm alone, so I'm going to take it off. All right. So thank you for joining. I'm going to briefly talk to you about my research and about some other general topics. And don't hesitate to interrupt me and ask questions. My name is Mathieu Joerger. My first name is French. My last name is German. I was born on the border between France and Germany, moved to the US in 2001. Spent 15 years in Chicago, another 3 years in Arizona, and I came here in 2019. And, so far I've been loving it, even though I've spent some time in my basement here. And my first slide is about the students in my lab, because in my lab and at Virginia Tech in general, yes, we do some cool research, but, most essentially, we build researchers. Okay, so the research is important, but the researchers, the people that we work with are the most important part of what we do, right? That's the mission of the university. So I keep that in mind in my own lab. And so you can see we have a good group. It's still growing. And my lab, my research is on autonomous vehicles. And autonomous vehicles carry the promise of safe, fuel-efficient, and time-efficient mobility for all. And our lab focuses on safety. How can we trust the sensor information in autonomous systems? So that's really what we focus on. I think you will have a chance to see overall what the Aerospace and Ocean Engineering department does. And you'll see that we look at so many aspects of aerospace systems and aeronautical systems and ocean systems. And so this is just one small aspect. My background, so I've been working for the FAA over most of my career in academia on precision approach of aircraft. So how can we land aircraft using GPS, using satellites that are 20,000 kilometers above our heads? And so we've developed methods to do this safely, to make sure that we won't have more than one crash in 100 million approaches. And my research interests are in using these safety methods that we've been developing for many years, using them for other applications and using other sensors, for example, using autonomous cars. And so this is the one slide that is a little bit technical, but I wanted to give you enough focus and enough depth to understand where the challenge is in my research specifically, and in every lab that you will find in our department, you have specific challenges that are addressed. And so in my work, the toughest part is to quantify safety. How do you quantify safety? Well, the way we do this, the parameters we use, we can basically summarize them using this example. So let me have the laser pointer here. So we take the example of an aircraft approaching a runway, and the FAA has, or the regulation authority has defined what a safe volume is, what we call the alert limit requirement box. And this is the volume within which it is safe for the aircraft to be. So you want enough, or you want that box to be tight enough that if you're off in your positioning, the landing gear is able to take the shock of your positioning error, if you will. And the width is basically the width of the runway. That's basically how this box is defined. So under zero visibility conditions, you're going to use some sensors to navigate because the pilot cannot see. And for example, if you use GPS, there's a risk that the aircraft is outside of the box when we think that it is inside. Right? GPS is not perfect. And so we can focus on the vertical dimension, the vertical coordinate here, and we can draw a probability density function of the error in the vertical positioning. And if you look at the dark red color here, that could be what the actual positioning error distribution would look like. So if you do 1,000 approaches, you do the histogram, it may look like that red curve. Now, this is just typical, very basic statistics for accuracy requirements that we have to meet when landing an aircraft. We look at 95%, the positioning 95% of the time. When we talk about safety, we look at 7 nines to 9 nines. So 99.99999% of the time, we want the aircraft to be within that box. And the problem is that satellites, even though they are very expensive, they're made with the best equipment, they have some level of redundancy, well, they're going to fail. And GPS satellites fail basically, or they are safe 99.999% of the time only. Okay, that leaves quite a lot of it leaves a couple of nines that you have to ensure. And so to do this, to detect the problems, the large errors, what we call faults, we have to build detection systems. And the challenge now becomes, how do we deal with undetected faults? Yes, please.
So this information is based purely on the sensors that are on the airplane. There are not like cameras or sensors that are in the runway or something in the airport. Is this purely based off on the sensors in the airplane, or?
So you will see that we use both. Okay, but anything that you use that is not on the aircraft is going to have a delay, and the delay, the communication delay, is going to cost you some. It's part of a more complex system that you have to deal with, and you have to evaluate it to be reliable 99.99999% of the time. Okay?
Yeah, okay. Thanks.
Excellent question. You're anticipating on a later slide. All right. So, and I'm going to quickly finish here with the technical aspects, but basically, what we have to deal with, we have to detect the larger than usual errors. And now, if I don't detect something, it doesn't mean that it doesn't exist. It just means I failed to detect it. So when we quantify risk, we have to take into account the risk of not being able to detect these rarely occurring events. And the best we can do to predict risk is to upper bound the risk. We have an upper bound. That's the safe thing to consider. We don't want to be optimistic. That would be dangerous. So we're a little bit pessimistic. But we cannot be overly pessimistic. For example, we cannot set our threshold so that it would send alerts all the time, or the system becomes useless. The pilot is not going to listen to the alerts anymore. So we have conflicting requirements of continuity and availability of the service that makes our safety cases challenging. So we have conflicting forces in a pretty constrained problem that we are trying to solve here. Yes, question?
I have a quick question regarding integrity. So from what I can understand, the integrity risk by definition involves undetected errors. Mm-hmm. And I imagine you might cover this on a later slide, but while we're discussing quantifying accuracy and integrity, can you also quantify the probability of what a problem would be if there was an undetected error? Like if there was something more likely to fail than something else, would you factor that into integrity as well?
Absolutely. Yes, that's a big part of the challenge. So the fact that you have a detector, a simple way to think about it is if you have a way to detect faults, it basically is going to set a limit on the size of a fault. A very large fault is very easy to detect. The real challenge is those faults that are large enough to cause you to get out of the safety box, but that are still small enough to go undetected. And that's really where the challenge in this work is. And we definitely take these into account, yes. Okay. And I think that's the main aspect that makes integrity different from accuracy. In accuracy, you don't have to worry about rarely occurring faults.
Thank you.
Okay, thank you. All right, that's my only technical slide. The other ones will be more general. Hopefully give you an overview of what we are doing. All right, so I talked about the size of that box. That box around the aircraft is pretty big. It's 10 meters above and below the aircraft in the best case, and up to 40 meters left and right during, at least to bring the aircraft underneath the cloud ceiling. So it's a pretty big box, 40 meters left and right, 10 meters above and below. You can understand this is not going to be good enough for an autonomous car. And in fact, there's an entire spectrum of requirements that are slowly maturing and coming together. So agencies all around the world are starting to agree on requirements for autonomous systems. And we are a part of this. And it's getting exciting because we are getting closer to the capabilities of having autonomous systems. And so we're pretty much dealing with that entire spectrum of applications. En route and landing of aircraft, coastal area, ship navigation, railway applications, unmanned air systems, autonomous cars. All right, one of our primary sensor, and it's close to me because I come from a lab whose advisor came from the lab where the father of GPS came from. And so pretty much in everything that I use, I have a GPS sensor. And also it's the most ubiquitous navigation sensor around. So there are more than between 3 and 6 billion GPS receivers around. There is one here in my phone. If you think about GPS, don't confuse it with the mapping interface and the traffic interface that is on your phone. This is, I don't know, property of Apple. It is not GPS. GPS only tells you your position. And so there's a space segment, the satellites, which you're all aware of. There's a user segment, which is the little chip, the GPS chip that is inside your phone. And the ones we use for our the aviation grade receivers are kind of a different beast than what's inside here. And then there's a ground segment also. So there is a bunch of stations around the world that are monitoring the satellites. They're also estimating the satellite positions because you need that information at your receiver to determine your own position based on the satellite position. Okay, so the satellite tells you its position and it sends a signal that gives you the distance between the satellite and yourself. And with that, you can solve for your 4 unknowns, which are your XYZ position and a receiver clock bias, that because the receiver is not time synchronized with the satellite. Was there a question from Zach?
I was going to ask what tau meant, but you just answered that, so never mind.
Yeah, great.
I have a question. What's let's say in the max height of a airplane, when the commercial airplanes, like what's usually the time that it takes from a satellite? I know it depends, but to the airplane, but what's like the usual time?
Super fast. I have no idea, fraction of a second. So 20,000 kilometers is where the satellite is, and we take into account the transit time in the calculation of the distance. This is very predictable.
Oh, okay, so it's not like a huge margin of error. There is.
No. And this is taken into account, right?
Yeah.
So the accuracy typically of GPS, it must be, the specifications must be around 1 meter, but around 5 meters, sorry, accounting for all the atmospheric delays and all the other things that can impact the ranging measurement, the measure of distance.
Okay, okay. Thanks.
Okay. All right. So if you have 4 satellites, you can determine your 4 positions, right? 4 unknowns, you need 4 equations. And so I'm not sure what I wanted to say with this other than that. So in an ideal world, all you need is 4 satellites. But of course, there are errors that are impacting the signals as they travel through the atmosphere, the ionosphere. You may have heard about it. It's an ionized layer of the atmosphere, the troposphere, closer to the Earth. There are errors in the estimate of the satellite position. It is not perfect. It's about 1 meter level accuracy. And then there are some reflections of the signal on the frame of the aircraft or on the ground that cause some additional errors. So you have an error budget to deal with, and that's why we reach about 5 meters of positioning error. And then you have these other things, these rarely occurring faults. So the specification is that once every 10 years, the satellite clock, which is essential, right? We measure the distance to the satellite by measuring the time it takes for the signal to travel from the satellite to the receiver. So timing is essential. So those satellites are time synchronized with highly stable clocks, atomic clocks, very expensive. You know, we couldn't have them at the receiver. That's why the receiver is not synchronized to the constellation. And so these clocks, once every 10 years, they drift. There's a sudden increase. It's not regular, of course. It's statistically speaking. And this is something that will happen. It's very difficult to detect. It's not obvious at all. Once every 10 years, we have 30 satellites. So every 3 times per year, you can have one of these drifts of a satellite clock that can cause an aircraft to crash. So it doesn't sound like much, 3 times per year, but if you crash aircraft 3 times per year, you will feel, okay, GPS is not really good. And so there are a whole bunch of methods, techniques, and augmentation systems that have been developed for GPS. And this is what I'm trying to show here. So the x-axis here is the coverage. So you have some systems that are available close to an airport, others that are available over North America, for example, and that would be the case of the space-based augmentation system. And then you have systems that are available worldwide, like these RAIN methods that I am working on. And different systems have different levels of performance. And what I have on the y-axis here, the alert limit, is basically the size of the box that you can put around the aircraft or the vehicle. Okay, so you can see we have methods here that will get us down to meter level, I guess, for the size of the box, and in terms of integrity requirements on the order of 10 to the minus 6, 10 to the minus 7. So the risk that is 7 nines or 6 nines, which would be 99.9999% of the time that you could ensure your performance. Okay, but of course, for the most precise systems, you don't have a wide coverage. All right, I think it's a good thing to know that there is a lot to GPS, a lot more than what you may think. And it's still a very much active area of research, and it's my community. You may also know that GPS is no longer the only constellation of navigation satellites out there. Russia has been operating GLONASS for many years. It has redeployed that constellation in 2014. And so, they are now in better shape than they were 10 years ago. Galileo is the European system that is now operational, and it offers more satellites, but also, new signal, new frequencies, which help to get better accuracy. And then China has developed Beidou. And so within a few years, we can have 25 to 35 visible satellites at all times, anywhere on Earth. Okay, so it's an area of research that is expanding. It's very exciting time to work on these, and we have very promising perspectives. If you add to that the fact that you have these internet, broadband internet constellations like Starlink, like a group of Virginia Tech alumni who developed OneWeb, or at least they're part of the founders for OneWeb. These communication satellites, so they're designed to provide communication. We are working on using them for navigation. So nominally, GPS has 24 satellites, Galileo 24 satellites. This constellation, the Starlink constellation, 3,000 satellites. Okay, so that opens new perspectives. Very exciting. I did my PhD thesis on using Iridium. That's another constellation of low Earth orbiting satellites that are designed for communication, but that we can use for navigation. Okay. Yes. Question.
I have a question. As the idea of satellites in orbit to help with autonomous vehicles increases, do you think the number of satellites needed to maintain that will increase as you need more coverage and will improve precision? Or do you think it will decrease as the satellites themselves become more proficient, like they won't need other satellites?
Well,
I was going to ask if they would increase or decrease.
Right now, the number of satellites is increasing. And because the coverage and the accuracy are two things, but we also need redundancy for higher integrity. So if we have more satellites, we can do this detection, the detection part that I mentioned earlier. For example, if you imagine having four, we need 4 satellites to get a position fix for GPS. If you have 5 satellites, now you can compare your solutions using the first 4 satellites, another subset of 4 satellites, another subset, you have multiple sets that you can compare to each other and do some detection this way. So redundancy is essential, and we try to have high redundancy of high quality satellites. That would be ideal.
All right. I didn't consider redundancy at first. Thank you for that.
All right. There are still lots of issues with satellite-based navigation, especially for autonomous cars in urban canyons. I studied in Chicago. There are areas in Chicago where you have no coverage of GPS because imagine being between 2 buildings, very high buildings. They're basically going to block all the signals that you can get, all the direct line of sight. All you're going to get are reflections of the signal that are, just completely corrupted with errors and delays from the reflections. So you get a position fix, but it's going to be way off. All right, so we are far from getting solutions. And so that means it's a very promising area of research. And that's one that I believe in. And so let's talk a bit about autonomous cars. So satellite navigation, that would be like your number one sensor for aircraft applications in particular. Very predictable, we can do great things. For autonomous cars, you have to reduce the size of the box, right? To stay within your lane, for example. And then you have to deal with a much more unpredictable environment with trucks passing by that are going to block GPS, that are going to occlude your radar or laser measurements. And then, of course, you can have weather also impacting this. So I've been looking at autonomous cars for many years. I come from a part near the Ruhr Valley in Germany, where you have all the car manufacturers, BMW, Mercedes, and so on. So that's where I did all my internships when I was in France. And so I've been looking at this. There have been many bubbles on autonomous cars starting in the 1960s. Can't see the right-hand part of my chart here. Can I do? No? Okay. All right. In the 1960s, there were these electronic highways. In the 1990s, there were magnetic beacons that were embedded in the ground, and that would help guide vehicles. But you could only do that over small stretches of roads. And then at VT, we have the Virginia Tech Transportation Institute, VTTI, which must be one of the 3 major transportation institutes in the US. And so it's pretty exciting. They have their own systems and they do a lot of testing. It's a pretty big institute. And so there's a lot of hype on these autonomous cars, and it may be discovered this hype cycle. And so this is valid. Whatever you do later, you will see that for emerging technologies, all emerging technologies follow a same trend. So you have this expectation chart here, the y-axis. This is very general, way beyond what my specific topic. Expectations on the y-axis, time on the x-axis, and the timeline here differs for every applications. And typically you have these 5 phases: an innovation trigger, where you see all the promises of the new technologies, and people think of lots of applications, lots of new things that you could do. Think about machine learning, artificial intelligence, all of this excitement. Oh, magically you're going to solve all your problems. And then you start seeing the first experimental validation, the first applications that show limitations to the technology. And so you reach the peak of inflated expectations. Now you have to start becoming realistic. And then you have the trough of disillusionment. Okay, well, maybe it doesn't work that well. Okay, autonomous cars, start seeing crashes. People even, getting injured or worse in these autonomous systems. And then there are a few of these technologies that are going to survive and rise again on the slope of enlightenment, and then, getting produced. So this is something you want to keep in mind in your engineering life. And this repeats itself over and over again. And I've followed that over the past 10 years. It's been quite interesting. And so this chart was from 2019. Autonomous driving is not even on the 2020 chart. Okay, so it's kind of came all the way through this cycle, and we don't really know if it's going to survive. But there are going to be lots of new technologies that are going to come out of all the work that has been done to try to get cars to be autonomous. And so if you want to think of these automated driving systems, what are their performance? It's difficult to judge. If you read the press, you hear all sorts of things. I'm French and American, so when I read the French newspaper, the president of Nissan Renault, which is the French counterpart, he was saying that we will have mass production of autonomous cars in 2018, and that was in 2016. So that didn't happen, and instead, we saw all sorts of incidents. On the top right-hand side chart here, you see the first collision where the Google car was at fault. The Google car is the white SUV on the top right, and it hit that bus. It was a very minor collision. Then there's the Tesla system. Here it was running on autopilot. You can see that it failed to see the construction to the left-hand side of the road. There was the tragic incident in Florida, the first death on a Tesla due to the autopilot, which it failed to see the white trailer. That didn't contrast with the white, bright Florida sky. And the car drove underneath the trailer. It decapitated the driver. The car kept going full speed until it went across 2 fences and finally hit a pole and came to a stop. When I was in Arizona, there was an incident with an Uber car that failed to see a driver. And so it's difficult to really know how well these systems are really performing, because we don't have all the data, of course. But one thing that can give us some perspective is if we look at the performance of human drivers, we would like these autonomous systems to be at least as good as human drivers. Well, human drivers encounter 1 fatality per 100 million miles driven. That's a 10 to the minus 8 per mile performance. That is extremely challenging to meet for a robotic system. So hopefully that helps you put this in perspective. Yes, question.
Yeah, but I guess that takes into account, like drunk drivers and people who like under the influence of kind of substances and stuff. So I guess that number, like the accuracy of like human drivers, will be higher now if that wasn't taken into account.
Yeah.
I don't know.
Yes, this number right here, it's a very low number, and yet 90% of this number is caused by the human driver. Okay, so we are extremely skilled drivers. I mean, if you compare to robotic systems, claiming that type of performance for a robotic system, it would be pretty amazing. And to me, it tells me human drivers, even the drunk ones that are not in this statistic, they're just excellent, very complex. It's a very complex task, and we are doing a great job overall as compared to robotic systems.
Yeah, thanks.
If you take a single component, we're not able to manufacture and mass produce single components with fault rates much lower than 10 to the minus 4, maybe 10 to the minus 5 per hour. The current efforts to prove whether autonomous systems are safe is basically to drive these autonomous cars over millions of miles, and Google, every year, they publish their results. They are now called Waymo, the autonomous car part. And they have driven, last time I checked, like they're probably at 10 million miles right now. But if you wanted to prove statistically that these vehicles are safe, you would have to drive, if you wanted to do it by pure experimentation, you would have to drive 5 billion miles. That is driving all the way to Neptune and back. Okay? I should give you some perspective on, if you're hoping to do this experimentally, I think it's pretty much a non-starter. So we're trying to develop analytical methods to do that, to prove the safety of the system, using the methods that we had developed before in aviation. And so this is an example of a test bed that we used in Arizona, and we've built the same here in Virginia Tech. We have a rover here driving on a figure-8 track, and we load it with sensors. In this case, we see here infrared cameras. That's a motion capture system, like in the movies, to capture the motion of the actors. So we have these little ping pong balls, or the retroreflective spheres that you see here. And we have some on the vehicle itself. We have a LiDAR that gives you a point cloud of the environment, an inertial sensor that tells you your linear acceleration and angular velocity along the 3 axes. And we drive this, and we can drive this for hours and hours. We turn it on in the evening, we leave, and we compile the data the next day. And we try to challenge our algorithms, for example, with different landmarks, with different colors, and landmarks that get hidden, occluded behind each other. And so that just shows you the vehicle moving. You see the landmark here, the white one gets hidden behind the black one. And we want to challenge the algorithm at that point and want to see if we can quantify the risk of mistaking one landmark for another, one cylinder for another. And yeah, that's what we're doing, right? Oh, we want to quantify the risk of mistaking these landmarks, and then we want to quantify the impact on our positioning error. Okay? And so this is just the raw data to give you an idea of the data you'd be collecting in my lab. We have radars. It looks much more messy, the data from the radars. We have GPS, of course, when we do experiments outside. And then we look at the data, of course, because this is a very structured environment, we can get very good estimated trajectory as compared to the true trajectory. Those red ellipses represent the spread of the error. You can think of a, I don't know, 70% spread. In 2D, it's a bit more complicated than with a 1D Gaussian. Anyway, it gives you an idea of the spread of the error, the orientation of the error distribution. And that's it. And then this is what we are providing to the community. An ability to quantify the risk, what we call PHMI, probability of hazardously misleading information. It's basically your safety risk versus time as the vehicle moves. And you can see here we have a sudden increase in risk because landmark number 3, I guess it's when we are at this point, landmark number 3 gets hidden behind landmark number 1, and there is a risk of mistaking one landmark for another. Okay, that's really what we wanted to capture here. And so number 1, our contribution is the ability to quantify risk with these new sensors. We do this analytically, so it doesn't take any time. We use equations, we use math. And number 2, we can look at the performance improvement with other sensors. And so we can design sensor systems that are going to be safe. So we use the LiDAR, we use the inertial data, and then we use the intensity return that we get from the LiDAR. The LiDAR is able to tell us if it's looking at basically a black or a white cylinder. All right, then we run experiments outside. I guess I have this included here mostly because I wanted to show you, this simple cylinder experiment is actually a pretty good representation in a structural scenario of what we see when we go. Here it's driving on the campus at Illinois Tech, which was our partner on this project. Okay, and we see we have occlusions and the tree trunks looks like the cylinders that we are extracting. Okay. All right. So these are the type of projects that we're working on. I would say the first project, the most exciting part on satellite-based navigation is that we work for the FAA. We are given a few bits on the GPS navigation message that all 3 trillion GPS receivers are able to capture and to decode. And we broadcast integrity information about basically the health of the satellites and how well they've been performing. Okay, so it's exciting to have such a global reach. We're also working with the MITRE Corporation on the problem of jamming and spoofing. So there are lots of interference. For example, the UPS truck driver, he doesn't want his boss to know that he's taking a detour. So he's going to use a jammer so he's not tracked. Maybe he wants to work, the truck driver wants to work more than 11 hours in a row. So he's going to turn on the jammer. There was an incident in Seattle where a company, they wanted to dump trash in the ocean without, paying the necessary fees to get rid of the trash. And so they would use jammers. And we have this problem of having these jammers, and they spread more and more. In fact, we've taken data in Roanoke, and we found out that twice a week, we see a jammer passing by the highway. So they're everywhere, even in our kind of remote locations here in Blacksburg and Roanoke. Of course, if you go to Washington, D.C., you see hundreds per week of these incidents. And how can we monitor that? The idea here, the vision is, can we build a weather map, but for radio frequency interferences that are impacting GPS? And we have networks of ground stations that have been operating for years. We have huge quantities of data, of this RF data. They've been deployed for scientific purpose, but we are using them to see when GPS gets jammed. And then we have all of these receivers on board satellites. So this is a screen capture that I took last night. And you can access this online, and you can see the air traffic. Okay, and we are going to use this to monitor RFI interference. And we're finding very interesting things. So there are some known events we know that have occurred. during the war in Crimea, we were able to find incidents because the military in Russia were using jammers to prevent positioning by the enemy. And then you can also use data from ships. And so last week I was watching the Ever Given, the ship that was in the Suez Canal here. So a lot of data that we can use. Yes, please, question.
Yeah, so basically what I understood here is that the way to find out if somebody is using a jammer is that the GPS or his location suddenly goes off. That's
Yes.
the way you can prevent that. Is that the only way that you found out to counter this?
Yeah. So, if you want to find these jammers, you need some RF receiver to measure the RF environment. And so we have all of these receivers that are already there, and we're trying to leverage that. So the jammers and the spoofing, they're going to have different signatures. A jammer could simply just completely deny service, or it could be more subtle. It could cause an increased error statistically, or it has many different manifestations. And so we have ways to detect jammers from these receivers.
Oh, okay. Thanks.
Okay. And that brings me to the end here. So yeah, we're using analytical methods in all of these cases to reduce the amount of field testing, talked about that briefly, to make decisions. So, we're going to tell the system, look, your safety risk is too high. You should abort your approach. You should slow down on your car, and so on. But also to design new systems, to design new sensor systems in the future to ensure that we have safe transportation. And yeah, that's pretty much what we do in our lab. And yeah, any more questions? Yes.
So from what I understand of the data I've seen here in this presentation, autonomous cars, it's easier for them to crash with an obstacle, say, but not a car or a person, but rather like a wall or something, or some post, or some, I don't know, some other obstacle that's not moving. Is that the case for autonomous cars, like accidents with those?
No,
Or is it kind of equal?
I don't know that this is the case. Okay, both have occurred. So in our work, we've been focusing on just staying within a lane, with the idea of a box. You have to stay within a box or within a tunnel.
Yeah.
And that's just our choice, because in aviation, that's what we started with. But the collisions have occurred, right? The Uber car in Arizona near Phoenix that collided in a pedestrian. These things have happened.
Yeah.
Okay, we have another question.
Yeah, my question is that the way I've heard about it, how people implement science is that you can determine with science whether you can do something or not, and whether you should do something or not. So in your line of work that we've seen in this presentation today, do you use the data at all to determine how autonomous technology is used, or are you just testing the capabilities and the probabilities of safe autonomous technology?
We're testing and we're designing new systems. I guess the beginning of your questions was a bit unsettling on science, so I'm not sure I'm answering here. We're trying to analyze data to see how well systems have performed historically, but we're also trying to predict how systems will perform based on the historical data, just based on the statistics. And we're trying to modify or improve the systems so that they will perform as we would like them to in the future.
Okay, that answers my question. Thank you.
Awesome. I want to tell you, since I arrived in Blacksburg just a few years ago, so I've been a bit around. I come from Tucson, is where it was way too hot. I'm just really loving it here. The colleagues are fantastic. At least, within the faculty, we have a very colloquial department. We all help each other. It's something that you rarely see. I've been in a few institutions now. It's a joy to be here, at least from a faculty point of view. My students so far are not complaining too much, but it's a great place to be. Yes.
Well, as a former European yourself, I wanted to ask something. What's the main difference that engineering colleges here in the United States have with engineering colleges, say France or Germany? What's the difference between like the average engineer that you've seen, your experience?
It's a different world. So it's really completely different. We have a lot of. I have many examples I could give you. In my engineering school in France, we built a controller for a project that was not very useful, if you ask me. And the controller itself was the size of a fridge. Okay, the size of a fridge. It was a huge controller where you had to plug in cables. That was in 2000. Okay, it was not a century ago. When I came in the US, I was given $50,000 to build an autonomous lawnmower. That's kind of the difference in the projects, And that project in France never went anywhere, even though we were 20 students working on it. And my autonomous lawnmower, it ranked third and second at robotics competitions. So it's just a completely different world. I think it's top-class research. There are fantastic labs in Europe. We work with Europeans and people from all around the world. But I guess in the US, it's just different. And there's also the fact that when you contribute to research, it is in an academic environment, but it's very professional. I mean, we write reports for companies. We don't only write papers.
Yeah, so you'd say that like American engineers or colleges of engineering here in America have like a more profound focus on applying stuff that actually work in the real world sometimes.
Well, I think you can find both.
Yeah, of course, but your experience.
Yeah, my experience was I found it very rewarding to actually apply things, to see, my code is currently being tested on GPS receivers on Airbus and on Boeings. That's incredibly rewarding.
Yeah, of course. Well, thanks for your opinion, your view on things.
Yeah, thank you for attending.
I have a question.
Yes.
How, in your career, how did you get to learning about this topic?
Excellent question. So I came in the US. At the time, I had used internet maybe 3 times. I was clueless about technology, in France, basically, we do a lot of math in my engineering school. And that's pretty much all I knew how to do. I barely knew what GPS was. I remember Googling it. Basically, I met my advisor at Illinois Tech, and he completely changed the course of my life, not only my career, my entire life. I went to the US just to do a Master of Science, and my advisor completely changed my life. I don't know how to tell you this. That's also what I loved here in the US, is the relationship, the mentoring, relationship that you get with your boss. If you find a good supervisor, it's a fantastic experience. It becomes a guide in your life. I mean, you cannot describe that. It's not a father, it's not a family, but it still structures your thinking and your it's much more than a professional relationship.
Yeah, I can understand that. That's actually very inspiring, and obviously why we all applied to Virginia Tech.
Yeah. So my colleagues are fantastic. I admire them very much. I'm very lucky to be here. I was very happy, I applied just like you guys did. Maybe it was even more a tougher application in our case, but I love being here. I'm sure whatever you do, you'll find something you like. So I came here. I didn't like navigation in particular. I didn't like GPS, but I've been loving working on it ever since. It's been 20 years.
Do you have any suggestions for us, like in terms of the major, when we go into our majors, like how can we tackle the challenges of our major and stuff? Like, in your experience as a firmware engineer, what were your suggestions, like in terms of for us, we're incoming freshmen?
Well, I had a pretty simple approach about this, and I'm not sure how you're gonna do this. Some people love space and they want to do space. Some people want, we're all different. In my case, I just wanted the challenge, so I just always went to the toughest, the field that had the toughest reputation, the most selective ones, and that's always what attracted me, and that's how I went to do what I'm doing. And it also matches my skills. I do a lot of math. I think most of these research, this is what's good about research. You're free to do things that you like. So you see there are experimental parts. I don't like doing experiments. I hate dealing with hardware. You have to deal with suppliers. They do crap job. It's a pain. But I do some experiment, but I also get to do all the math that I love. So I think you get freedom when you I guess the more you advance in your academic career, the more you get opportunities to do things you like. Oof. I'm not sure.
Say that not be afraid to get challenged and what do you like? What would be your suggestion, basically?
Yeah, I think most engineers are driven by challenges.
Yeah, of course.
And so, yeah, I've just always been seeking the toughest challenges I could find, I guess. I got very lucky to find my advisor. I was very, very lucky. All right, guys, I think that's probably the end. I'm guessing you have other events following.
Yeah, it was a pleasure.
Thank you.
I'm glad to be here.
Yes, this was very nice and very informative on a niche topic like this. I really appreciate it.
Excellent. Well, it was my pleasure. Thank you for the questions. I'm gonna just show you my email address if you need anything. Don't hesitate to send me a message.
Thank you. That was really interesting.
It was actually. There's so many ways this topic can be used. So this is very insightful.
All right. Choose Virginia Tech. You cannot go wrong. It's great.
Go Hokies.
Hope to see you on campus later on.
All right.
Bye.